Great. Okay, thanks, Gordon. Right, so my name's Ian Morris. I'm an applications engineer in the microcontroller business unit located here in San Jose. And after Gordon's introduction to the 4300 family, I'm going to talk a little bit more about some of the peripherals he touched on and the memory architecture. So just an overview. We've seen this one before, but we see we've got the Cortex-M4 and the M0. And the M0 is something I'm going to talk about in detail. I can talk about the memory, particularly the flash and the SRAM. And then we're going to talk a little bit more detail about things like the serial GPIO, the SPI flash interface, and some of the configurable peripherals that really set this device apart and make it really flexible. So let's start off, and we'll talk about the flash memory and the embedded on-chip SRAM. So we've actually got two banks of flash memory, up to a maximum of 512K bytes each, depends on which part you buy. And the really neat thing about these is you can actually use it in this dual mode. So they're two completely independent banks of flash memory. So you can run code out of one, and you can erase and write the other. And this allows you to do really reliable firmware updates. So in the past, you'd have to copy something into RAM, and that algorithm would write to flash. No longer. You can use your code that's in flash A and write to flash B. If you get a power fail while you're updating your firmware, that's okay. The contents in flash A are still valid, and at boot up, those will be used. Only when you're happy with the contents have been written into flash B do you invalidate the flash A image, and at boot up, you'll start running out of flash B. So highly reliable flash updates. The other nice feature about the flash memory are these flash memory controllers. So we can run the core up to 150 megahertz, but running at that speed, you need wait states to access flash. So what we do is we have these flash memory controllers. So when the CPU requests an instruction or some data out of flash, it's only requesting 32 bits. But the flash memory controller goes away and actually gets 256 bits and buffers the rest that you don't need. So next time you come back, assuming you want to get data from a consecutive address, it's already there. So no wait state going into flash, and you get it immediately. So this really gives you a good performance boost when you're running at 150 megahertz out of flash memory. The other thing to say is, of course, you dual mode, but you could just simply view it as two 512 banks of flash and 1 megabyte area. So the SRAM, got a huge amount of SRAM on this device, 264K bytes maximum on the biggest part. And there's actually some thought gone into the organization of the SRAM. It's not just one big bank of SRAM. So the bottom two blocks, 128K bytes and the 72K bytes, you can actually execute code out of. So although we've got the flash memory controller that accelerates operation out of flash, if you really want true zero wait state access and code execution, you can load your code into one of these large areas and execute out of there. And you're still left with a large amount for data storage. So really, really flexible architecture. The other thing to note about the SRAM is the way it's connected to the bus. So these are on separate parts of the bus matrix. So you can your CPU could be executing code out of this part of SRAM. And for example, your ADC via DMA could be taking readings and dumping data into one of these data-only areas of RAM. And what that means is you've got no bus contention. They're on separate areas of the bus. You won't see a performance penalty on your code execution. So it's really well, the SRAM, I think, is really well optimized for DSP use when you're going to be wanting to run zero wait state execution out of RAM. So next we're gonna take a really brief look at the internet. Brief look at the USB and the Ethernet that's available, and then we'll take a little bit more in-depth look at some of the configurable peripherals. So okay, USB. So we've got two USB 2.0 interfaces. One of them actually contains an on-chip PHY, so you don't need any external components to achieve a high-speed USB interface. The other one is full speed and contains a full speed PHY on chip. If you want to convert that into high speed, it's capable of doing that, and we've got a ULP interface for connection of an external high-speed PHY. So really you've got two high-speed USB interfaces and you just need one external PHY. So a really low-cost solution. The Ethernet, Ethernet's pretty standard. We've got interfaces to an external transceiver, but there's some quite nice features as well. Hardware checksum in of TCP/IP packets. It's got its own DMA controller for really high-speed operation. And plus we've got this 1588 timestamp in hardware built in. So the M0, this is, I think this is one of the more exciting features of this part, because I believe this is one of the first kind of dual-core devices, certainly the first M4 M0 core device available on the market. So let's take a look at the thinking behind this first. So the idea really is that what you want to do is you want to use the M0 to free up the M4 for what it's good at. So the M4 is really good at DSP-like applications, image processing, running a control algorithm. And the way we see it breaking down is the M0 is going to take care of the real-time control aspects. So it's going to use your peripherals, it's going to run maybe protocols, etc., and deal with the real-time aspects. And it's going to free your M4 up so you can get the absolute maximum processing out of it possible. So here's a little bit of detail about how it's implemented. And I think there's a couple of key features, and the first one is the fact that what we're trying to represent in this diagram, both the M0 and the M4 are connected to the bus matrix, okay? And what that means is that they've both got access to all the peripherals and all the memory. So there's nothing the M4 can't do, the M0 can, in terms of peripherals and memory. They've both got dedicated NVIC controllers, so they can both handle interrupts independently of each other. The M0's got a lower number of interrupts, so it only supports, I think, 32 interrupts, but it still supports interrupts from most, if not all, of the peripherals. We had a question earlier about the clock rate, and absolutely right, the M4 and the M0 can be clocked at 150 megahertz, but you can actually tune the clock. You can divide the clock down on the M0. So if it's not doing a particularly intensive task, you can clock it down and reduce power consumption. You can also, obviously, power it off completely. If you're not using it for a period of time, turn it off, save yourself the current. The final thing to mention, I think, is the message queuing system. So we've got an API for IPC, interprocessor communication, built into the on-chip ROM that provides a mechanism for you to easily transfer messages between the two cores. So you don't have to think about that, how you want to implement that. There's an API in ROM that uses the on-chip RAM in a way that you can pass messages easily without any contention. So what are we doing? What are we doing with this? And we mentioned before we've got a demo, and it kind of highlights all our demos highlight the split, the division of labor, as it were, and how we see this working. So again, the M4 is doing the heavy-duty processing. So in this application, you can imagine a USB connection to maybe a PC, etc. We're sending packets, audio data down to the M0, and the M0's handling the protocol, maybe issuing acknowledgements, stripping off packet headers, etc. And then it's passing the raw audio data over to the M4. The M4 is then free to process it, doesn't have to worry about doing anything else, servicing USB interrupts or anything. Passes it back using the IPC to the M0, and the M0 can output it on the I2S to a headset or other audio device. So we see the clear division. The M0 is dealing with the peripherals and the real-time aspects. The M4 is simply running your algorithm. So you're going to be able to get your best out of your M4. And what this means is you can either run a more complex algorithm than you would if you didn't have the M0, or the other way of looking at it is you can actually clock the M4 at a slower rate to achieve the same results and hence reduce your power consumption. So another quick example, and this is very similar to the example we've actually got out by the demo station. So we've got the M0 in this example. The M0 is looking after the CAN interface. I think in the demo it's actually looking after a UART. So it's taking commands from a PC that's running a GUI. It's issuing acknowledgements and looking after the protocol, passing those commands across to the M4. And the M4, in combination with the SCT, is controlling a motor. So doing all the PID control, etc. So again, a real division between what these are doing. But the kind of difference in this one is showing that, yeah, the M4 can actually use the peripherals at the same time as the M0. Okay, so it's not just a processor for audio or control algorithms. They both have equal access to all the memory and all the peripherals. So development. There's one JTAG port, and they're both connected to the one JTAG port. So you decide which one you want to debug, you download your code, you single step through one or the other. In terms of software development, you really consider them as different processors. Okay, this is how we're doing things at the moment, is you've got two different projects. It's almost like have two different processors on the board. You develop your N4 app, your M0 app, and download and decide which one you want to debug. So it's really, really straightforward. Okay. So let's talk about the SPI flash interface that Gordon touched on earlier. So it's actually, conceptually, it's really straightforward, this interface. So what we have is we have a serial flash memory externally, and normally you have to talk to it over a SPI interface, and you clock data out, clock data back in. What the SPI flash interface does, it allows this serial flash memory to appear as a block of internal memory. So the M4, when the M4 is looking at it, it can talk to this serial flash memory, read from it, simply by reading internal memory address. So this really simplifies communication with these serial flash memory type devices. And importantly, because it just looks like a normal piece of internal memory, it can actually execute code out of this serial flash memory. So no need to copy your code in to internal RAM and execute it from internal RAM. It can be executed directly out of the serial flash memory. And the performance isn't, you don't take a performance hit that you might think. These devices, we can actually transfer data at up to 40 megabytes per second from these serial flash memories. And we'll see how that's possible in the next slide. The way we do that is to use quad SPI flash. So you can use standard SPI flash, and everybody's probably familiar with the pin out of a standard serial flash memory. We can actually hook up quad SPI flash. What quad SPI flash does is we just replace the write protect and the hold lines on a regular serial flash memory, and they become 2 more data lines. So you've actually got 4 data lines on a quad SPI flash device, clock out 4 bits per cycle, so you can actually get a lot of data out of these very quickly. And I believe that the LPC4300 is the first micro on the market that has support for quad SPI flash memory. Now, you know, a lot of people look at these and go, oh, that's okay, I can execute code out of it, so I can have a flashless device, but these devices are expensive. Well, actually, you know, we found they're being used on PC BIOS, PC motherboards, so the prices are really coming down, they're really competitive, which is why, as Gordon said earlier, you could think about using a flashless device and a serial flash memory to execute your code directly out of that device. So what would you use this for? If we take a look at an example, we might get an idea a little bit more of how useful it is or how it can be used. You know, we've got an LCD controller, and what you normally do, obviously, with an LCD controller is you've got to store the image somewhere. It's output to the LCD controller from DMA, but it's got to reside somewhere, and it's usually either in internal SRAM, or more likely, if you've got a big graphics display, in external SDRAM or SRAM. And you know, that solution's a little bit expensive. You've got buy a chip with either a lot of SRAM on board, or you've got to add an external device. You've got a bigger board. You've got to lay out the tracks, etc. to it. So we can see the solution using the SPI flash interface. Okay, the SRAM's gone out of the question. We've got the external serial flash memory, just a little 8-pin device, just about 6 signals to it, connected directly to the SPI flash interface. And because this allows that memory to appear as a big block of internal memory, we can just set the DMA controller up and say, fetch data from there and send it to the LCD controller. DMA controller is not aware that it's going via SPIFI, it's just using an internal block of memory. Okay, so what that means is, like I said, no SRAM, a low cost or a low board space solution. And I'm sure there's many other problems you can solve with a serial flash memory, especially seeing as you can execute code out of it. This is just one example. So the supported devices. I think this is kind of the title's a little bit misleading. Supported devices. It's hardware. The hardware actually supports just about any device out there. It's a quad SPI interface or a standard SPI interface. It's pretty standard. What we really mean by supported devices are the drivers. So in the on-chip ROM, we've got some drivers for each of these devices. And those drivers simply allow you to make a call to configure the SPI flash interface really quickly. Okay, so instead of working out how to set up the registers in our SPI flash controller to talk to each of these different devices, we've got a driver. Make one call, tell it which device you're using, sets up the registers, you set it going, and the external memory appears as internal memory. So that was the SPI flash interface. Any questions on that? I think it's fairly straightforward, but still I think it's a really interesting and neat feature.
Quick question. So the SPI interface, you're saying it's like 40 megabytes per second.
Mm-hmm.
So it's still slower than the internal flash.
Absolutely, yeah.
So we're not going to expect to run the CPU at 150 megahertz at full speed when using the external flash.
No, you're not going to get the same performance. You're absolutely right. If you're running the CPU at 150 megahertz and running out of internal memory, you'll have a lot more performance than executing code out of the external SPI flash memory.
So for the internal flash, when you're because you have 256-bit interface, right?
Mm-hmm. Yep.
You have like 8 cycles, or you can run the internal flash at 8 times slower speed than the CPU to have the real-time performance. Is that correct?
I'm not quite with you.
Your CPU is running at 150 megahertz.
Yep.
You can run the flash at internal flash at 150 divided by 8.
Where's the
megahertz.
divide by?
Wow, it's almost like 20 megahertz, and then you still get the real-time performance.
Well, we don't know how many wait states yet. We haven't finished characterizing, so it's not divide by 8. I think it's about 2 wait states, 150 megahertz.
So what is the actual speed for the internal flash?
Well, it's about the access is about 2 wait states, so 2 150 megahertz cycles.
2 150 megahertz.
Yeah, so you've got to wait about 2 cycles. We're still characterizing, but you've got to add about 2 cycles delay before it responds.
So you're running the internal flash at 75 megahertz?
Yeah, it's not actually clocked from anything. You know, you just go and access it, and it's this long before it presents the data back.
So which solution, like internal flash or external flash, which solution is more power efficient?
That's a good question. We don't have the figures yet. I would imagine, I don't know. To be honest with you, I don't know what the external SPI flash current consumption looks like. But certainly the performance isn't going to be as good. What we're going to do, we're going to actually, because we use a core mark to benchmark our cores, and we publish core mark figures. So we're going to do a core mark figure based on running out internal RAM, 0 wait states, flash at 150 megahertz, and maybe a few different frequencies. But 150 will be the most interesting. And then we're also going to do the core mark running out to the external SPI flash with the interface running at 40 megabytes per second. We'll publish those figures, and hopefully those will give you an idea of the relative performance difference that you can expect.
Thanks.
Okay. Okay. Sorry.
Can the core write to the SPI flash?
It can program it through a special. It doesn't look like normal read-write memory. It doesn't look like RAM because it's flash. It's got to do some cycles, etc. But it can write, yeah. So the SCT, the State Configurable Timer Subsystem. So a basic, a really simple way of looking at this is the fact it's a timer coupled with some state event logic, and there's actually 16 outputs available. So there's 16 outputs that are coupled to timers with the state event logic. It's also associated, got 8 inputs associated with it, and the logic internally, 32 states, 16 events. We'll see what that means in the next slide. What it really means is it's a more complex PWM kind of block, timer block. See how it works. This is probably a better way of describing it. So on the left-hand side of the screen, we can see it's a standard timer. So we've got a pre-scaler, the up-down counters, the match registers, and this is normally where a normal timer would finish. Just here in between, that's normally where you generate your interrupt, or you change the state of your output to generate your PWM. What we've done is we've added this state event logic onto the end of it. So the timer now actually generates an event into this logic block. And we can generate events from other places, from other peripherals, from GPIO, etc. And what that event can do is that event can then, depending on how you configure this, can start another timer, can change the state of an output, can generate an interrupt, and it can do that based on state. So if it looks at the state and says, oh, at this time the state's 1, 2, 3, I'll start this timer, I'll capture the value in that timer, etc. So it can make simple decisions. So what you can see is once this block is set up, you can generate waveforms, you can react to inputs, all without the CPU having to interact. The CPU could be actually in doze mode, it could be sleeping, and this thing can run and can timestamp events and can change the state of outputs based on timers or the state of inputs. So development, it's quite a complex block. So development's got to be quite rigorous. Design your state event diagram first, like you would with software, and this will then directly map to the registers, because we have registers that represent states and events. So if you design this carefully with some thought about the registers, you can then almost transfer it directly, write your code to set the registers up. And as I said, start the SCT, you could shut your CPU down and it will run, it'll generate waveforms, react to inputs, etc. We're actually going to have a library of examples available. I think one of the first ones is going to be the motor control demo that we've got running out in the hall. I think it's field-oriented motor control being run by the SCT, and the CPU just really doesn't have to take very much action at all. So the I think the last one we want to talk about, the serial GPIO function. So again, a simple analogy. So it's a GPIO coupled with a timer and shift register block, and we've got 16 of these. And I think it's really neat because it means you can easily generate patterns on your I/O. No more having to bit bang, no more having to sit in loops, setting an output high, doing a few no-ops, setting it low, and just load up the registers with the patterns you want and clock the data out. As I said, 16 inputs or outputs, so you can clock data in as well as out. And the really interesting feature as well is 3 states for the outputs. So obviously you can set output high or low, but you can also set it into a high impedance state. So on one clock cycle you can actually set it high impedance rather than high or low. You can see immediately, well, oh, I can emulate things like I2C then, okay, because I can set it high impedance, let the other end pull down to do an ACK. So very, very flexible and powerful unit. Here's the internals. We'll just go over this briefly just to show some of the features that are available. So the first thing is you can obviously, there's a timer with a prescaler on it, so you can control the rate at which data is clocked out. Pretty obvious. The shift registers that clock the data out are 32-bit shift registers. But there's another register that you can control the number of bits you clock out. So you don't have to clock out all 32, you can clock out 1, 2, 6, 7, etc. There's also some shadow registers. So as soon as you finish clocking out the number of bits you set it to, automatically reload to the next data to be clocked out. You've got another set of registers that control the output enable state. So this is how you high impedance the states. So for every output bit, or every bit that you output, you've got a corresponding bit in the output enable register. So you're on a bit level basis, you can say high, low, or high impedance. You can also, another neat thing is you can concatenate these together. So if you've got maybe a pattern, a 56-bit pattern that you need to repeat, you can concatenate shift registers, hook them up together, generate your 56 bits. So what's this used for? I think Gordon mentioned earlier, but I think we've all come across them. I came across an LCD driver recently that I thought was SPI. First examination, actually it turns out it's not. It's a completely proprietary interface, and the vendor actually supplies code for you, pseudocode, and says this is how you need to bit bang your outputs to drive this LCD. So what you'd normally do is, okay, in software, high, low, no ops, etc. And it's really going to occupy your CPU. It could be 100%. You've got to sit there. You can't really have interrupts going because they might cause latency in your output waveforms. If you're using the SGPIO, it's no problem. Set up your waveforms, clock data out to the device, clock data back in, And all you're going to get is an interrupt occasionally when the shadow registers reloads the output register, just like in a UART when transmit's complete. You're going to get the interrupt saying, I need some more data, or I've clocked your data in. Really reduces your CPU load time. The other really interesting feature, I think, is you can mimic a standard interface. So not just some weird proprietary interface, but say you find on the device, oh, okay, you've got one I2C, but I need two. You can configure this this peripheral to be another I2C interface. So you can, I think it's good to bear this in mind when you're looking through the spec sheet. You might think it hasn't got enough peripherals that you want, the right mix. It probably has. This is a really powerful, flexible block. Now, what we're going to do is we're going to provide a library of examples, and I think these listed here will be the first. So make it easy for people who want to add another I2S port, another SPI port, download your example, it'll configure the registers, and you're good to go. Question?
If I implemented an I2C using this, would it be more energy intensive as a block than a dedicated I2C cell because it's more general and there's extra stuff that has to be configured?
Yeah. We've not finished characterizing it, but I think you're absolutely right. Yeah. There's probably wouldn't be a lot in it, but the I2C there's a lot less logic in there. It's dedicated to that one function. Okay, so thanks for your time.